Good afternoon, everybody. We are here to finish out this first section of the Anatomy and Physiology Review. This is a three-part video presentation on the nervous system. So without further ado, let's get started. So when you think about the nervous system, you need to think about it being an electrical pathway. So we're dealing in electricity, we're dealing with a quick fix. Think about flipping on a switch. Unless you've got a dimmer switch, if you just flip on the switch, the light comes on really quickly. So think about the nervous system with quick fixes, quick responses. When we have a patient who's been involved in some sort of traumatic injury and we're quick to arrive on the scene after the incident has happened, their nervous system is what is responsible for maintaining that homeostatic balance. If the patient has been chronically ill, they've been sick for a long time, or that injury has been ongoing for several days, we're doing maybe an inter-facility transfer. In those types of situations, then it's probably not the nervous system that's trying to maintain homeostasis anymore. You start looking at another thing called the endocrine system, and it deals in chemical messengers. So it's all about chemicals for long-term maintenance of that homeostatic balance. But when things happen immediately, our body's first reaction is to utilize the nervous system in order to maintain it. So the nervous system is a very extensive network of cells. They connect information to control and coordinate all the functions of our body, and it's more commonly, as I mentioned, referred to as an electrical pathway. Now we do have two divisions. We have the central nervous system, which is comprised of the brain and spinal cord, and then you have the peripheral nervous system, which is pretty much everything else. But what a lot of people don't remember or have a tendency to forget is that the cranial nerves, despite the fact that they are housed up there really close to the brain, the cranial nerves, along with those spinal nerves, are considered part of the peripheral nervous system. So we're going to start the discussion by looking at the peripheral nervous system first. And remember that our peripheral nervous system, again, is comprised of cranial nerves and spinal nerves. We have a total of 12 pairs of cranial nerves, 2 that are actually coming from the cerebrum, and then you have 10 pairs that arise or come out at the level of the brainstem. Now this picture, if we were to cut the skull cap off of somebody, pop the skull cap off, take that brain, pull it out, turn it upside down, this is what you would see if you flip the brain upside down. You would see all of those cranial nerves that are connecting and helping with everything from a sense of smell all the way through to our balance and use of shrugging our muscles and so forth. So those are your 12 cranial nerves. Yes, you do need to try to remember what those are for and attempt to commit them to memory, because you do see those come up periodically on National Registry. But I just like this picture because it shows you where those cranial nerves actually exit this, as it comes off the spinal cord and out of that area. And this is just another side view. It shows you how that those spinal nerves, you can see C3 and C4. You can see how those kind of come off of the cord as it's running through the neck. You can see the foramen magnum. Now remember, the foramen magnum is the hole at the base of the skull that allows the spinal cord to come up and pass through. This gives you a chance to kind of see how that accessory nerve that we talked about a minute ago, how it comes out, and you can see how it innervates the shoulder muscles. So that gives you a good idea of how that works. Now here is the list of the cranial nerves 1 through 12. I know this list is terrible, but you'll have to probably pause the video, enlarge it if you can, take a minute to write it down. But they're arranged in terms of what they impact. So you can see the glossopharyngeal, which is number 9, is also connected with number 12. So glossopharyngeal is about tongue movement, taste, swallowing, also involved with blood pressure maintenance, so forth. The hypoglossal is also about the tongue muscles. So I kind of connected those together so that you could, um, you know, um, you know, kind of understand what they were supposed to be for. And the same thing with the oculomotor, the trochlear, and the abducens. All of that has to do with eye movement and eye control. So I've combined those together up there. So you can see the number 4 and number 5 are kind of moved and migrated around some. Now we're going to look at the vagus nerve on the next slide because it's going to be one of those things that we kind of hit on. The vagus nerve, it carries your impulses that are related to speech, swallowing. It goes from the pharynx and goes to the pharynx and the larynx, from the viscera of the thorax, and from the abdomen to the brain. But the big thing that you need to know here is that the vagus nerve is what tells the body to slow down. So we're slowing our heart rate down. Those are the different things that kind of happen with that. Now you also have the spinal nerves. We're going to look at those. And the spinal nerves, if you have these mixed nerves, they provide communication between the spinal cord, the neck, the trunk, and the upper and lower limbs. This is a little picture to kind of show you how that rolls through. And you can also see how the spinal cord ends in what's called a cauda equina, or a horse's tail. And so that kind of gives you an idea of how that spinal cord stops and it kind of becomes this bundle or branching. And you can see how they exit to travel down the legs through the sacrum. Now, when it comes to the spinal nerves, they correlate very closely with the number of vertebrae that we have, with one exception. The cervical vertebrae, you have a total of 7 cervical vertebrae. But when it comes to the spinal nerves, you actually have 8 pairs that arise from the area of the cervical spine. Then you have 12 thoracic, 5 lumbar, 5 sacral, and 1 coccygeal, 1 paracoccygeal. And it can't be medicine unless we continue to subdivide things down and make it harder, right? So we're going to talk a little bit more about the subdivisions of the peripheral nervous system, because it directly relates to what you're going to do on the truck as a paramedic. So you have the peripheral nervous system that's divided into a somatic and an autonomic nervous system. So when you think soma or somatic, you need to think skeletal muscle, because that's what you're controlling here, skeletal muscle. On the flip side, I'm trying to use my pointer and it's not, there we go, somatic nervous system. Again, that's skeletal muscle. I want you to think of it in that terms. Now, you're also dealing with other things here, but look at the name. This is autonomic. We do not have control here. That's really important. The somatic nervous system, you have some control, and I'm going to say some with a big asterisk attached to it because there is a point here that I'll make in a minute. But then the autonomic nervous system, you have no control over. These are automatic functions within the nervous system. So when you talk about somatic, it gets further broken down into 2 categories. You have the pyramidal, and then you have the extrapyramidal. So we're going to look at this on the next slide. When it comes to the pyramidal, and this is where I said most, and I put that big fat asterisk in there, because we don't have voluntary control over this type of skeletal tone over here. But our pyramidal system, we have conscious, voluntary motor control of our skeletal muscles here. Extrapyramidal, these are outside of our control. So if you've ever had, well, I think I go into it on the next slide, so I'm going to hold that thought. So why do we care? I'm going to talk about why we care. You have a thing called extrapyramidal motor syndromes, also shorthanded as EPS. Hint, hint, wink, wink, nudge, nudge. You may see a question about this on National Registry. Extrapyramidal motor syndromes, or EPS, are typically caused by some of the antipsychotics and medications that patients are prescribed, and things that we can see that are being utilized out in the field. Your phenothiazines are notorious for causing EPS. One of the medications we carry that could cause EPS is Phenergan. Now, Phenergan's kind of fell out of favor because we've got other things that do a better job, but Phenergan can cause extrapyramidal syndromes. And it's because it's blocking the dopamine in the brain, and it can cause things like a shuffling gait, rigidity of extremities, they can have drooling, or they could even have weird little muscle twicks or spasms or little dystonias, if you like to use that word. So if you ever have a patient, and usually the scenario plays out that you've got a patient that's really nauseated, they've been vomiting a lot, you go ahead and you give Phenergan, you're reassessing your patient, and you see that the patient is starting to have muscle dystonias and drooling or something like that. They'll give you some little weird trigger, and what they're looking for you to do is know how to reverse that. You don't have to know the dose. Normally, all they're going to ask you is, what is the name of the medication? What is the reversal agent to treat EPS? The answer to that is Benadryl, your diphenhydramine. Now, on the flip side, we talk about the autonomic nervous system, and it gets further subdivided into the sympathetic nervous system or parasympathetic. So it's either the fight or flight or the feed or breathe. So your sympathetic is your fight or flight, parasympathetic is your feed or breathe. Now, this is how we're going to connect these to your job, and this will make a little bit more sense. And we're just going to give an example, some here. I'm not going to go into a whole different bunch of medications. We're just going to use some that you guys should be familiar with because you've seen them if you've been working with a medic. But your medications that we give on the ambulance don't do anything magical. They either enhance or inhibit natural processes in the body. So when we start looking at medications, you have epinephrine. Epi makes you peppy, right? Epinephrine mimics that fight or flight. So it will stimulate the fight or flight response. Atropine is a little different. Atropine works against the, my apologies, I had my phone ring, so I wanted to take care of that. Atropine works kind of against the parasympathetic nervous system, and it doesn't work against it. It's called a parasympatholytic. So if you think about epinephrine as trying to speed up the system, we're doing a fight or flight thing, we're trying to make you peppy. That's like hitting the gas pedal on the car, okay? In the case of atropine, you've got a patient that's, they've stopped, they've slowed down, they've come to a complete stop. If you've come to the complete stop, you probably have your foot on the brake, right? So with atropine, what atropine does, it allows the fight or flight to take over on its own. It will actually it's kind of like taking your foot off the brake pedal. And what happens to your car if you let your foot off the brake? Your car starts to coast forward. So it's the same concept here. Atropine is kind of inhibiting or trying to pull away, allow that parasympathetic response to walk away. So you're allowing, as a result, you're allowing the fight or flight to take over of its natural accord. We can use an example here of medication administration in the case of an organophosphate poisoning. So if you have an organophosphate poisoning, if you've heard the term sludge, salivation, lacrimation, urination, defecation, gastrointestinal distress, and emesis. You may have even heard sludgem because it has to do with the pupils of the eye. But in an organophosphate poisoning, we are intentionally, that poison is intentionally triggering the parasympathetic nervous system. It is trying to make it overactive, okay? And as a result, we salivate because remember, parasympathetic is feed or breathe. So if the parasympathetic nervous system is taking over, then as a result of the organophosphate poisoning, you've got excess salivation. They're going to tear up. They'll snot. They'll drool. All those things that you would associate with a feed or breed response is what you're going to see this excessive exaggeration of in an organophosphate poisoning. So the way we do reverse that, there's two agents. One, there's a thing called 2-PAM or 2-pralidaxione. That is a specific medication that goes in and tries to pry that organophosphate loose so that the body can pick up and do what it's got to do. The only problem is when it can't pry it loose if it's been attached for too long. We'll talk about that later. It's not extremely important right now as long as you understand the concept. Your atropine is your other medication that you give. So you end up giving 2-PAM and atropine. That's part of that Mark 1 kit, if you remember the old Mark 1 kits. But the atropine helps to allow the fight or flight to take over of its own accord. So we're going to review neural anatomy. Now, don't lose yourself in the weeds here trying to memorize a lot of this. It's just to kind of give you a better understanding. It's not necessary for you to memorize. I'll point out the things that you need to recall. But you do have different classifications of the nerves based on where they are located, what they do. So you have unipolar neurons, and the unique thing about the unipolar neurons is you have these little dendrites, and then you have the axon, and you'll see the cell body of the neuron actually sits up and out of the way, and that allows that travel down the axon and on to send it on to other nerves or muscles or organs, as the case may be. So unipolar is all about the sensory nerves. That's where you have the sensation that is on the, I'm trying to think how to put this. So let me see if I can use a pen. So if you have, and we'll go with a red. So if you have a nerve that's traveling up, it's traveling up to the spinal cord. So if you had the brain and you have the spinal cord coming down, wow, that is a terrible spinal cord. But anyway, this information that's traveling up, that's your sensory information. So you've touched something and it is sending that signal up to be interpreted. So it's going up to the brain and spinal cord to be interpreted. That's where your unipolar neurons come into play. Now, on the flip side to this, your motor neurons are responsible for moving that information. So once it's interpreted, so here the brain and the spinal cord again, once that information is interpreted, it sends information down to the muscle to move away. So if you think about it, if you've ever touched a hot stove, that information goes up, it gets interpreted, and you usually jerk your hand away, and that's what we want. That's the motor polar or the multipolar motor neuron that we're talking about here. So you have the unipolar that is sending information up, and then you have multipolar that is sending it down. So you kind of wonder, like, why would we make that differentiation? Why would our body be created that way? The information that is traveling up is all coming from small branches and it's moving toward a center, okay? But when it's coming away from the spinal cord and it's telling you what to do, not only is it coordinating the muscle movement here, but it's also sending a signal to your brain that's reminding you of the last time you burned yourself. It is sending a signal to your mouth so you can screech and probably cuss and raise 3 shades of hell because you've touched something, and you're going to jump up and down and you're going to bounce, and all of that is because that multipolar neuron, which is not a unipolar, that multipolar is coming down the line. Look at this. We've got our dendrites. The information comes in. The cell body happens to be right there. Travels down the axon, and it's branching off to go to different areas. Now, the special one of the group is the bipolar neuron. The bipolar neuron is only found in 2 particular spots: the hearing and vision. Those are the only two places where the bipolar neuron exists, or that structural classification. So I decided to take the multipolar neuron and use it. So this is part of our motor neuron. It's sending information down, telling us to move away from the threat. So there are three major parts. You have the dendrites. The dendrites are receiving the impulse. It is traveling around or through that cell body, and it comes down and sends the signal down the length of the axon. Now you'll see that axon is covered with this little sheath, and we're going to talk about the sheath here in a minute. We'll kind of come back to that. But then that signal comes down here to the dendrites, or excuse me, I'm sorry, my apologies. These are dendrites. These are dendrites, guys. These are synaptic terminals. Sometimes they're called synaptic knobs, but it all means the same thing. So you have that signal that's traveling down to these synaptic terminals, and it's sending that information either to the motor, to the muscle. Sometimes they'll call it an effector organ because you're creating an effect. You want something to happen. So it's sending information to the effector, and that is how the nerve is played out. Now there is another type of neuron called an interneuron, and the best way to kind of perceive this, first, those interneurons are only located in one spot. They're located within the brain and spinal cord, and they're kind of like the interconnector. So they're responsible for analyzing the sensory information that's coming up the side, and it's sending out the signal on the motor neuron side. So it's kind of like if you've ever had the 3-prong to a 2-prong adapter, that's what you're doing. You have this sensory information that's traveling up, it plugs itself into that interneuron, and then the multipolar neuron is on the other side. Sorry, I should get where you can see me. The multipolar multipolar neuron is coming off the other side and traveling down and sending the information out. So that information is getting translated and interpreted there, and it goes on down the line. So here's an interesting thought for you. Did you realize that the majority of our activities that we do every day is actually interpreted and handled at the level of the spinal cord? Now I'm going to give you an example, and until I tell you this, you wouldn't have paid attention to it, because we have a thing called the, oh shoot, hold on. Sorry, I had to take a pause and think the word I was trying to think of instead of making you have to wait on me. You have a thing that's called the reticular activating system, and that actually decides what information is important enough to go to the brain for processing. So you may have that information that travels up that says, hey, moron, you're touching a hot stove, you need to do something about it. It does not have to go to the brain and spinal cord for processing. It actually gets handled at the level of the spinal cord, at that interneuron, sends the information down on how to handle it. So when you start thinking about the reticular activating system, it is actually filtering out a lot of the information that's coming in on a constant basis. So I can give you an example of that. Until I've told you this, you wouldn't have thought about it. But our brain is really good at filtering out unimportant information. Until I mention it, you wouldn't have noticed it. Your sensory nerves are picking up the sensation of your clothes touching your skin. Now, until I just said that, you probably didn't notice the way your clothes were actually touching your skin. Because now that reticular activating system has said, well, maybe this is important, and it moves it out of the way, and now your brain is consciously aware of it. But prior to that, it was filtering that signal out. It wasn't important. Now you do have these things called glial cells, and they provide structural support for the nervous system. There are 5 types. Again, do not get hung up here. This is not the end of the world if you don't have them memorized. You've got astrocytes. These are the ones that are responsible for the blood-brain barrier. You have oligodendrocytes. Now, if you remember, I mentioned that axon had a sheath on it. That, excuse me, those are what create the myelin sheath to kind of protect that nerve. And we'll talk about the disease pathology that can impact the myelin sheath here shortly. Then you have things called the microglia. These guys have phagocytic type cell properties. They kind of keep everything clean. The ependymal is the one that is responsible for producing the cerebral spinal fluid. And you have Schwann cells. And the Schwann cells actually will cover every axon that exists outside the central nervous system. So just to kind of give you a picture of the way that looks, how that kind of plays out. Now we're going to talk about impulse conduction. So we're going to look at how those impulses travel. We already touched on this. I may have to stop here in a second, give me something to drink. But you have sensory neurons. These are your afferent because you're touching something. After you touch something, an event will occur. So afferent is before, efferent or event is after. So sensory neurons are sending information from the periphery, the peripheral nervous system, sending it up to the brain and spinal cord for processing. Remember, you got those interneurons there. And then it sends that information down the motor neuron or the multipolar neuron to tell the muscles and the body, those effector organs, tells them what to do. So that's the direction of travel. And we want to know how that information is getting passed on. And this is where talking about that myelin sheath kind of comes into play a little bit. So there's two ways that cell conduction can occur. And you have the sodium potassium exchange pump, and that's where you have the electrical impulse that happens when you have a continuous conduction. You have a nerve that the axon does not have a myelin sheath. So if you look at the picture of the nerve at the top, there's no myelin sheath covering that axon. It's kind of exposed. Okay. In order for that impulse to travel, it literally has to depolarize the entire length of the axon. Okay. It takes a long time for it to travel down through. That's called continuous conduction. If you have the myelin sheath, so you have the protective covering, then the only places that are having to be depolarized are the spaces between those little myelin sheaths. So this is called saltatory conduction because it bounces from one exposed area to the next. So you can imagine that saltatory conduction will move a heck of a lot faster than a continuous conduction. So if you wanted something to kind of give you a reminder of it, you're looking at this continuous conduction because it has to depolarize the whole length of the axon. It's kind of like dealing with Eeyore. He's very slow. He takes his time. He's always the last one in the line. But if you have Tigers like to bounce, and that's what you see happening here with the multipolar neuron in particular, but you got this myelin sheath, and it allows that signal to bounce along the line. It's a lot faster. So I hope this kind of helped. I am going to go ahead and mention what happens here before I go away. The myelin sheath in a condition called multiple sclerosis. It is an autoimmune disease, so our body recognizes the myelin sheath as foreign, and as a result of it recognizing it as foreign, it tries to attack it and break it down. So the disease that results from that attack and breaking that myelin sheath down is called multiple sclerosis. So kind of think of the myelin sheath as you would a extension cord that you have outside. It's got that thick outer layer that protects the electrical power coming through. It keeps it nice and contained. If you have a break in that, you can imagine that electricity will come out and zap. So think about your patients that have multiple sclerosis. They are not able to control their muscle movement, and it's because that myelin sheath is being destroyed and that electrical impulse is not traveling down the line like it should. And that is all for this video. I know it says wait until next week, but that's okay. Next week is coming as soon as you cut this video off and decide to move on with the presentation. Have a good one.